In previous chapters, we've talked about the composition of the atom, and it's worth reviewing here really fast. So an atom has a nucleus in the center of the atom. In the nucleus are the positive protons and the neutral neutrons, and around it circle, if you will, the electrons in the electron cloud. Electrons behave more like a wave that kind of envelops the nucleus and extends right on around, while the nucleus is very, very small, all right? If that was actually the size of an atom, the nucleus would be probably something so small we couldn't see it here in this picture. So it's pretty small. There's a lot of energy in the nucleus. So when it comes to the reactions within the nucleus, it's going to be much higher energy. And so the reactions in this section will look quite different from the previous chapters that we've seen. One of the results of nuclear reactions is radiation, and radiation is just a really high energy form that emits sometimes when reactions happen. Radioactive rays can penetrate and ionize matter, so it'll go through the matter and it will turn them into positive or negative ions, which isn't good, of course, for the structures. Radioactivity was originally discovered by Becquerel, and then later Marie Curie really took that ball and ran with it and did a lot more work on radioactivity. Radioactivity is pretty important. Even around us right now, we are experiencing some radiation. If you live on the Earth, and I'm assuming you do, then some radiation comes from the Earth up to us. Some radiation comes from outside the Earth to us through the sky. So it's a really powerful tool, and we're used to some radiation. So we'll talk in this section about what radiation is, what it can do. Also talk about the types of reactions that create the radiation. On the periodic table, there are at least 3 really important portions that we've talked about before, but let's go through them again. One of the things that's really important is the atomic number, given the symbol Z, and the whole number listed to each element on the periodic table is the atomic number, and the atomic number is just the number of protons. So for aluminum right there, aluminum atoms always have 13 protons. So the atomic number is 13, aluminum has 13 protons. Those two things go together. However, you can have more than one version of the same element, and this got us into isotopes. So to figure out isotopes, we need to talk also about the mass number. And the mass number, which gets the symbol A, is equal to the protons plus neutrons for the nucleus. So as an example of this, boron is number 5 on the periodic table. That means it can have 5 protons, no problem. But boron can have 5 neutrons. We'll talk about why it sometimes doesn't have that too. So if you want to figure out the mass number for a boron atom with 5 neutrons, protons plus neutrons, 5 plus 5, 10 would be the mass number. And that symbolism in the lower right there shows AZ, you can see that the upper left-hand corner is the mass number, the lower left-hand corner is the atomic number, and then the symbol goes kind of right there in the middle. So that would be the symbolism for boron 10. And sometimes the atomic number isn't showing because the hip chemist knows that boron with symbol B always has 5 protons, an atomic number 5. So sometimes the 5 is omitted to just have the superscript. Just kind of realize these are all the perturbations you can have. Now, because there are different isotopes, there are different versions of boron, for example. So boron 10 is around a lot, but there is actually a boron 11. So a boron 11 is a different kind of boron. It's an isotope of boron. The reason that boron 11 would be different is that the mass number A for boron 11 is 11. Now, boron always has 5 protons, so 11 minus 5, mass number minus atomic number, tells you the number of neutrons. So boron 11 has 6 neutrons. So while we just talked about boron 10, there is also a boron 11 with an extra neutron. The third piece of information for each element in the periodic table is the atomic weight, or the molar mass of the particular element you're looking at. So for aluminum right there, that's 26.9815. If you look at boron on the periodic table, it's roughly 10.8. And the atomic weight / molar mass number comes from the fact that it takes all of the isotopes and thinks about the abundance. So boron 10 is roughly 20% 20% of the abundance of all boron atoms. So what that means, if you had 10 boron atoms, 2 of them, 20%, would be boron 10. But 80% or so are boron 11. So for the 10 boron atoms we have, 2 of them would be boron 10, and 8 of them would be boron 11. So all of those numbers together gives you the atomic weight / molar mass number of boron, which is about 10.8. So for aluminum there, it's about 27. All right, aluminum 27 is the most abundant isotope. There is, for example, some aluminum 26 and stuff like that. But notice how the atomic weight is very close to 27. That a lot of times is a hint as to what the most abundant isotope is. Great segue to this question. Copper can be found in 2 primary isotopes, copper-63 and copper-65. Which isotope is more abundant? It might be tempting to think more information is necessary, but what you can do is just look at the periodic table for copper. Now, copper's number 29. That's the atomic number. Copper has 29 protons. And here we're talking about 2 isotopes of copper, copper-63 and copper-65. If you look at the value for copper on your periodic table, it's about 63.5. And 63.5 is closer to 63 than it is than 65. You can think about like a number line between 63 and 65, the 2 mass numbers. Then the average mass, which is listed on the periodic table, 63.5, would be closer to 63 than it is to 65. So for all of those reasons, copper-63 is more abundant. Copper-63 is roughly 70% abundant, and copper-65 is about 30% abundant. And those are not things you need to know, but that's why the average mass, which is the atomic mass or molar mass, is closer to copper-63 than it is copper-65.